This work concerns future urban airspaces, which will be home to numerous autonomous air taxis, package delivery drones, and more. Urban winds are unique spatial and temporal flow fields that present a clear and present danger to urban flight operations. To enable autonomous urban operation, it is imperative that these aircraft are aware of these wind patterns, but existing estimation schemes degrade in cases where a map is outdated, the location of the robot is unknown, or the operating region has dynamic obstacles. To that end, we present a method for predicting wind patterns in a region around the robot based on local context. Our method leverages deep learning to achieve real-time prediction rates, an attribute that makes it highly appealing for applications in wind-aware path planning and optimal control. A highlight of our approach is that no prior knowledge of the building geometry is necessary. Inference is instead accomplished using immediate information about the surrounding buildings provided by range measurements. To enable rapid training data collection and experimentation, we wrote an unsteady Eulerian fluid solver in Python, which was validated against experimental test cases. Then, we trained deep neural networks on time-averaged wind flow through small, procedurally generated maps with random wind conditions. However, in our results, we challenged the generalizability of the networks by evaluating them on much larger maps with over 200 buildings. In these simulations, we provide insight into the real-time predictions that would be offered by our method when operating within the training distribution. A robot is programmed to fly between a set of waypoints using its onboard LiDAR to sense nearby buildings. At a given instant, the LiDAR scan is combined with measurements of the wind both upstream and at the robot's location to predict the surrounding wind vector field. Our deep neural networks learn consistent representations of the time average flow field, meaning that flow reconstruction from our method is surprisingly robust to robot translation and sensor noise. Safety critical wind patterns such as channel flows, corner accelerations, and even building wakes are accurately predicted by our networks despite very limited knowledge of the map. In fact, our networks can leverage patterns in the training data to predict flow around corners and behind buildings, even though these regions are occluded. As seen here, our method can also be applied to arbitrary prediction grid sizes. A primary focus of this work is training generalizable mappings from local context to local wind fields. Hence, in this simulation, we visualize the network's performance on a map outside of the training distribution. Flow reconstruction worsens as the robot enters denser regions of the city, which are quite different than what was seen in the training dataset. Despite this, important flow features are still predicted by our method, indicating a surprising amount of generalization for our networks. We expect that adding denser maps to the training dataset would improve the model's performance in these settings. As the robot flies into less dense regions upstream, flow reconstruction improves. Our method will enable real-time reasoning about complex wind patterns, leading to safer and more efficient autonomous flight in future cities.